Hello everyone. Today I'm going to talk about almost optimal sublinear additive spanners. This is a joint work with Zihan from Rutgers University. Let's begin with a general notion of graph specification. Suppose we are given a graph and we want to find a smaller graph with similar shortest path. For example, on the left-hand side, we have a somewhat dense graph, and we want to specify this graph in some ways so that for any shortest path in the original graph, we can find a similar shortest path in the specified graph. Let's formulate the problem more specifically. Suppose the input graph is unweighted and undirected, and let H be a candidate spanner, which is a subgraph. We are interested in two parameters of this subgraph: the number of edges in this graph and the stretch function. We say that this graph H has a stretch function f if the distance between any pair of vertices is at most f of their original distance in graph G. In general, when the sparsity is smaller, the stretch function becomes worse. So our goal is to understand the optimal trade-off between sparsity and stretch. Let's first consider the case where the stretch function is large, say linear in the distance. In this case, the parameter t is called the multiplicative stretch of the spanner. An upper bound was first proved by Aviv et al. In 1993 that for any odd integer stretch, there exists a spanner of size n to the 1 plus 1 over k. More importantly, this construction is tight if we believe the Irish-Girth conjecture. Other than multiplicative stretch, we can also study small additive stretch, where f is very close to identity function, only up to a constant error. Here is a list that summarizes our current knowledge regarding spanners with small additive stretch. When the additive stretch is 2, in a paper by Einworth et al. In 1993, they constructed spanners of size n to the 1.5, which matches a subsequent lower bound by Woodruff in 2006. For additive stretch, Chechik in 2013 constructed spanners of size n to the 1.4, which has not been improved ever since. For 6 additive stretch, Basmana et al. Had a construction in 2006 with n to the 4/3 edges, which was complemented by a strong lower bound by Abbott and Baldwin, which rules out any subpolynomial additive stretch with better sparsity. Besides the two extreme choices of linear stretch and small additive stretch, there are other stretch functions in the intermediate regime. For example, we have linearly additive stretch where f is equal to 1 plus epsilon d plus beta, and sublinear additive stretch where f is equal to d plus little of d, and purely additive stretch where f is equal to d plus little of n. Here n is the number of vertices in the graph. When the stretch function is nearly additive, where f is equal to 1 plus epsilon times d plus some exponential function of k, we have nearly optimal constructions and matching lower bounds. Namely, for such kind of stretch functions, the size can be made poly k times n to the 1 plus 1 over 2 to the k plus 1 minus 1, which was shown in a paper by Elkin and Peleg in 2001. And the lower bound shown in a paper by Aboud, Baudouin, and Petit in 2017 is almost the same. Our knowledge about sublinear additive stretch is not as complete. When f is d plus d to the 1 minus 1 over k, the best upper bound was shown by Petit in 2009 that spanner sparsity is at most n to the 1 plus 1 over some exponential function. For the special case where k equal to 2, there was an improvement by Chechik in 2013 that the sparsity is at most n to the 20 over 17. On the lower bound side, it was proved by Aboud, Baudouin, and Petit in 2017 that spanners for such stretch functions must have edges at least n to the 1 plus 1 over 2 to the k plus 1 minus 1. So this is the same as the nearly additive case, but here the parameter k has a different meaning. Therefore, there is an exponential gap on the exponent for sublinear additive stretch spanners. As our main result, we almost closed this gap with a better construction of sublinear additive spanners. The third type of stretch function is called purely additive stretch, where fd is equal to d plus little of n. Namely, the additive arrow does not depend on d. In this case, spanners can have linear sparsity. So the question becomes, what's the best additive term if we restrict ourselves to linear sparsity? There have been studies on both the upper bound side and the lower bound side. On the upper bound side, the first non-trivial upper bound of n to the 9 over 16 was given by Petit in 2009, which was improved later to n to the 3 over 7 by Baudouin and Vasilevska-Williams in 2016. On the lower bound side, the currently best lower bound is n to the 1 over 7 by Baudouin and Hoppenworth in 2022. As our secondary result, we improved the upper bound slightly from 3 over 7 to 0.403. For the rest of this talk, I will discuss a toy example where f is equal to d plus root of d, and how to achieve the optimal sparsity of n to the 8 over 7. After that, I will briefly discuss how to generalize it for larger k. Let's begin with the first part. Our algorithm relies on a lemma from a previous work. This lemma says, given any radius parameter r, there exists a set of balls in the graph with three properties. First, the radius of all balls are roughly r. Secondly, the union of all balls covers the entire graph. Thirdly, even if we double the radius of each ball, the total size of these balls is still almost linear. For the rest, the yellow area will be called the core, and the red area will be called the shell. To build the spanner, we consider different distance scales separately. Given any distance parameter, which is a power of 2, apply the previous lemma with parameter r equal to root of d. Then look at any shortest path whose length is d. We will use a set of balls to cover this path. This is done in the following manner. First, find a ball whose core covers the starting vertex S. Such a ball exists because of the covering property. Then, find the rightmost vertex inside the shell along the shortest path. Next, find a core that covers this rightmost vertex. After that, again, find the rightmost vertex within the shell, and so on. In general, we find a core that covers the previous black vertex, and then move on to the rightmost vertex on the shortest path, still inside the shell. Now, because the radius gap between the core and the shell is at least root of d, we know that the distance between the two consecutive vertices is at least root of d. Each time we find a new ball, we move forward for at least root of d steps. Since the total length is d, the total number of balls in this picture is at most root of d. To construct the spanner, we will only use the shells. Find a +6 additive spanner within each shell, which takes b to the 4/3 edges. If we're lucky and each shell has size at most n to the 3/7, then the spanner has size at most n to the 8/7. About the total stretch, we can take this dotted blue path, which accumulates an additive error of 6 within each shell. Therefore, the total error is at most 6 times the number of balls, which is order of root d. Now, what if there are large balls? To handle large balls, take a random vertex set of size n to the 4/7, which hits all large balls with high probability. In this picture, let us take 2 large balls on the shortest path, which are the leftmost and the rightmost. Then, there are random pivot vertices in both balls. To find a short path from S to T, it suffices to find a short path between these two pivot vertices. Then we can first travel from S to the first pivot and use the blue curve to reach the second pivot, and then to reach T. To preserve distances between yellow pivots, we apply the same ball covering approach on their shortest path, and to look for detours that suffer constant error within each shell. So it breaks into subtasks of preserving each blue segment up to a constant error. Let's focus on a single shell and change the choice of the pivot pairs. When the pivot pair changes, we produce different segments inside this shell, like this one and this one. In the end, we want to add some edges within the shell that preserve distances between these segments. This is a weaker requirement than standard spanners, which preserve all pairs' distances, especially when the number of segments is small. More specifically, it is clear that the number of segments is at most s squared. With a more careful analysis, we can show that the number of segments is actually linear in S. Now, it is natural to introduce the notion of pairwise spanner. In a graph, together with a set of demand pairs, a pairwise spanner has stretch function f if the distance between any pair in the demand pair set is bounded by f of their original distance. In a paper by Kavita in 2015, it was shown that for a 6 additive stretch, we can always build a pairwise spanner of size n times p to the 1 over 4. When p is quadratic in n, this is n to the 1.5, which is even worse than standard spanners. But when p is small, this bound becomes better. Returning to our scenario, if we apply the pairwise spanner, then the number of edges that we use inside this shell is at most b times s to the 1 over 4, which is at most b times n to the 1 over 7. Summing over all shells, this gives the correct bound of n to the 8 over 7. Next, let's discuss how to generalize it for larger k. Our previous algorithm for the base case of k equal to 2 relies on this theorem by Kavita in 2015, which constructs 6 additive pairwise spanners. For a general sublinear additive stretch, the only missing component is a pairwise spanner with sublinear additive stretch with n times p to the 1 over 2 to the k edges. To design a sublinear additive pairwise spanner, let's review the algorithm by Kavita. To build the spanner, there are 2 preparatory steps. First, add all edges incident on low degree vertices in the spanner. Here, a vertex is low degree if its degree in the original graph is at most p to the 1 over 4. Secondly, take a random vertex subset of size n over p to the 1 over 4, which dominates all high degree vertices with high probability. Take a look at the shortest path below. Here, each high degree vertex is adjacent to a random pivot, which is drawn as a yellow cycle. 2 pivots are called settled if their distance is already preserved by our spanner. That is, their distance in the current version of the spanner is equal to their original distance up to a constant additive error. For example, if these 2 pivots are settled, then there is a good path in the spanner between them. The algorithm considers 2 complementary cases. In the first case, if there are many pairs of pivots on the path already settled, then we can find a bridge structure. The bridge consists of 2 pairs of settled vertices with 1 common pivot in the middle. More importantly, this bridge structure is only n over p to the 3/4 edges away from both sides, s and t. Then, if we add a prefix and suffix of the shortest path of at most n over p to the 3/4 edges to the spanner, we can find a cheap path from S to T. In the second case, if most of the pivot pairs were not settled yet, then we simply add the entire SD path to the spanner, and in the meantime creating a lot of newly settled pairs. To summarize, for each demand pair, either we only add a small number of edges to the spanner, or we add the entire ST path, but in the meantime settle a lot of new pairs. Balancing the two terms, we can obtain the right bound. To generalize this algorithm for larger k, apply the ball covering lemma with radius r equal to d to the 1 minus 1 over k minus 1. Then use these balls to cover the ST path, which naturally decompose the path into shorter segments. As an analogy with the base case where k equals to 2, we can view each ball as a pivot and each segment as a single edge. As before, let's consider two complementary cases. If many ball centers are settled, then we can add a small number of segments to reach a bridge structure. Otherwise, we will add all of the segments while settling a lot of new pairs of ball centers. Here, when we add a segment to the spanner, we're not directly adding the subpath. Instead, we will assign this segment as a demand pair to the ball around it, and then build a pairwise spanner within this ball in a recursive manner. One technical difficulty behind this scheme is that balls might have different densities. The approach we have just described only works for uniform ball sizes. To fix this issue, we will divide densities into a constant number of classes and deal with each density class separately. I am not going to explain this further. To summarize, we have achieved almost optimal trade-off between stretch and size for sublinear additive spanners, if the parameter k is a constant. One remaining question is if we can remove the dependency on epsilon and also achieve better dependency on k. Thanks for your attention.